Okay, so let's start. So, good evening. Today we will be discussing assignment number 8, and I'll be sharing my screen. Yeah, okay. I hope you can see my screen.
Yeah, yes.
Okay. So we'll be discussing some. So this is assignment on load flow studies only, continuation of that, because it is such a large topic, and I hope assignment 9 would be dealing with this fault analysis, and that's one of the, I mean, the important topic, I guess. So we'll be coming to that next week, and we will be ending this load flow, I guess, this week. So now let us look at. So if you remember, in the previous week we were mainly dealing with these what um, I don't. I mean, we had only one problem on Newton-Raphson, right? So this week, at least 4 to 5 problems we will be seeing on Newton-Raphson, and only 1 or 2 problems probably on this decoupled load flow, and yeah, that's it. So yeah, let's start. 1 minute. Check. Okay. So let's start. So the problem number 1, the figure below shows the one-line diagram of a simple power system with generators at bus 1 and bus 2. Okay, so if you see the diagram, this is bus 1 and bus 2, and the voltage magnitude of bus 1 is adjusted to 1.04 per unit with an angle of 0. The bus voltage magnitude at bus 2 is fixed at 1.05 per unit with a real power generation of 100 megawatt, and a load consisting of 300 megawatt and 150 megawatt is taken from bus 3, and a load consisting of 200 megawatt is taken from bus 2. So base value is your 100 MVA, and they are telling key using Newton-Raphson load flow determine del Q3 by del V3 and del P2 by del 3 of the Jacobian matrix during the first iteration. Now, before going to that, just look at this diagram. So as you know, we have to consider one slack bus for our measurement purpose, but if you see this bus number 2, it is what, the voltage is fixed, right? And we have the this thing, real power, so it becomes a PV bus, right? On the other hand, this bus 3, it is a PQ bus, because we have the this active power and the reactive power. So I mean, looking at this, we can somewhat construct the Jacobian matrix, right? I mean, the what would the matrix look like? So let me just write that, and then we will go to the problem. So I hope you can see this notebook here.
Yeah, yes.
So yeah, so somehow we know that this matrix would be looking like this. Now we have to, for our analysis, we have to consider bus 2 and 3, right? Because slack bus is 1, so it's out of our consideration. Now what is known at 2 bus 2? It is your the um, the real power and the voltage, right? So what is unknown? It is I mean Q and delta, right? So okay, now we can here write this. So this would be what, del 2, and also if you see, so it is also the same for bus 3, right? So for bus 3 we don't know what is the load angle at bus 3. So similarly, del 3 is also not known. And we also don't know what is the reactive power at bus 2, right? These are the unknowns. And what are the knowns? So the knowns are the power at the real power at bus 2 and 3, right? So this would be what del P2 and del P3, and also we know what is the reactive power of bus 3 since that is a PQ bus, right? Now we can construct what would be the Jacobian matrix, right? So it would be, I mean, if you know how to write a Jacobian matrix, so this would be del P2, del 2, del 3, then okay, sorry, I have done a mistake, I guess. 1 minute, huh? Okay, so no, these are all the parameters of bus 2, right? So yeah, I have made a mistake here. So this would be what we don't know what is the also the voltage at bus 3, right? So this would be that, because the right hand side this matrix composes of the delta values and the voltage, right? So this is wrong. So this would be what um, delta mod v3, right? Yeah, and hence we can construct this. So this would be your delta v3. So here there would be a mod, and in this way we can go on writing the matrix, and at the end you would be seeing that it is a 3x3 matrix, right? And in the previous assignment you saw how, I mean, there was a problem on finding the order of Jacobian matrix, and I mean after constructing it you can see that it is 3x3, and also from the this bus diagram you can see that there is one this PQ bus and one PV bus, right? So this is PV bus and this is PQ bus. So the order was the formula was 2 into your PQ plus 1 into PV. So this is 2 into 1 plus 1, right? So 3. So therefore it is 3x3. Anyway, so this is how we will construct this thing. Now, I mean, having constructed this, and I mean, for each of these problems we have to find what are these components. So for example, if you look at this question, they are telling us to find what is del q3, del v3, del this thing, del p2, del 3. So these are the various components that are there. So now let's start. So I mean, for starting these kind of problems, we have to first construct what is the admittance matrix. We have been given this all of these components. So Z12 is J.0125. So I mean, you will get what is the Y matrix, right? It is, I mean, very easy. We have seen a lot of time. So Y11, capital Y11 is minus J18, Y12 is J8, Y22 is minus J33, Y23 which is equal to Y32 is J25, Y33 is minus J35, and Y31 is J10. Now, so they have told ki assume a flat start for the load flow. Therefore, and we don't know what is the magnitude at bus 3, right? It is unknown. That is why it is a PQ bus, right? So we assume that the voltage 3 is 1 per unit, and since we don't know what is the load angle also, we assume it to be del 2 is 0 and del 3 is also 0 degrees. So now we now yes, the base MVA is 100 MVA, and so the power at bus 2 in per unit would be what? Generation minus consumption. So 100 minus 200 divided by 100 is minus 1 per unit. And S3 there is no generation, so it would be what, 0 minus 300 plus I mean whole of plus J1 150 divided by 100, we get this. Now these are the assumption, right? Assumed values. Now we have to, using this formula, we have to calculate what is the actual value or the calculated value. So here you know the voltages and every component you know, right? Y22 everything we calculated, and del 2 to theta 22, sorry, you also know. So theta 22 would be what? Y22, right? So minus 90 degrees it would be, because minus the 33. You calculate every one of these. So V2 is what? 1.015. Your V1 is 1.04. You know delta 1 it is 0, and delta 2 we have assumed it to be 0, and delta 3, okay, delta 3 is also 0. So okay, you do this, and it is very easy. It comes out to be 0, right? Because each of these components, it is 90, right? Theta 21 is also 90, theta 23 is also 90, 2 is also 90. So it comes out to be, P2 comes out to be 0. Therefore, what is this correction factor that we use? So delta P2 would be what? Your assumption minus calculation, right? So it comes out to be -1. Now what they have told, so anyways, we won't require in this problem, but since question number 1 to 4 is a continuation, so we would be requiring it at some stage. Now what would be delta P2 del 3? You just differentiate this equation partially with respect to del 3. You get this, and you put all the values. It comes out to be minus 25.375 per unit, and it is there is a value here. So you see, I mean option here, sorry, yeah, this option, sorry, del P2 del 3. And we also know what is the formula of Q3. Now there is a minus because S, the apparent power is I mean it is, as you know, it is P minus JQ, right? So minus that thing comes here, and you have this formula, you put everything here, it comes out to be Q3 is minus 0.775. So what would be delta Q3? This I haven't written here. Delta Q3 would be your Q3 assumption, which we calculated. Where was it? Yeah, it was okay. This was minus J 1.5. Don't take this real term here, because these are, I mean, Q3, right? It is a reactive part, so we have to consider the imaginary term, right? We won't take the real term. Oh, sorry, this is S3. Sorry, my bad. So Q3 would be 1.5, and you then subtract this. It would come out, your del Q would come out to be something 725.725 per unit. Okay. So now we have to find in the question, we have to find del Q3 del V3, right? So del Q3 del V3 would be what? Just the partial differentiation of this Q3, equation number 3. You get this, you put all the values, it comes out to be 34.225 per unit, which is your option number B. So this is how you, I mean, we have calculated what a part of this Jacobian matrix, right? So in this way, we will be completing that matrix. So this was the problem number 1. I hope this was clear.
Yeah, yes.
Okay. Now let us go to problem number 2. So same problem again, they are asking. So same diagram as you see. So here they are asking, using Newton-Raphson method, determine del P2 del 2 and del P3 del V3 of the Jacobian matrix during the first iteration, right? So yeah, I mean, you again differentiate this P2 equation with respect to del 2. You get this, you put the required values here, and you get this to be 33.8198. So 33.82 basically. And what P3 would be, what you have this value, right? You know this equation, and you they have told us to find what del P3 del V3. So this comes out to be 0, right? I mean, pretty straightforward. So so this is your option number C. So now let us go to this question. Yeah, here they have told what would be the bus angle of bus 2, sorry, bus voltage angle of bus 2 after first iteration. Means if you remember, for starting the problem, we had assumed a value of delta 2 to be 0, right? I mean, it was, I mean, this should be what? Del 2 0, because it is at the 0th iteration. Now they are asking what would be the value of del 2 after first iteration, right? So del 2 1, superscript may 1. So, yeah. Now, for doing this, yeah, we require this matrix, right? Because we have to solve this, right? So I'll be taking you through this step by step. So components, right? Out of the 9 components of Jacobian matrix, we have to calculate the remaining 5. So one of this is del q3 del 2. So you differentiate it, it comes out to be 0. Now del q3 del 3, it also comes out to be 0. And del q3 del v3, it also comes out to be 0, right? Now here I have written this. So this is basically what, if I take you back, so this is del p2 del p3 and del q3, right? These are the values here, and this is the Jacobian matrix. So each of these values I have just put here, and this is this matrix only, this one. Now we calculated, right? Del p2 we calculated, so it was your -1 we calculated. Now what would be your del p3? So here I have written -3. It is mainly because, see, your p3 was -3, right? S3 is -3 plus j 1.5. So this is -3, and um, we are, assuming a value of so yeah, we are assuming a value of 0, right? So that is why it is 0 -3. So I mean -3 basically. So that is how, and I told you this would be -7.712. So you just do it on your own while you are solving the problem. It is very easy, you will get this matrix, right? Now we just have to calculate what is the value of delta 2. For that we need this del 2, right? For this, so I mean, it would be pretty lengthy if you do it this way, right? Because if you solve this, you will be getting 3 equations, you have to then calculate the unknown. The other way around is that you take the inverse of this matrix. When you take the inverse of this matrix, you get this matrix, and directly you can calculate the delta from here, del 2. So it comes out to be what? Minus 0.1976 radians. It comes out to be 11.32 radians. So it is what, after first iteration it would be 0 plus this value. So it comes out to be minus 11.32, which is your option number what? Yeah, C, D, I guess. Yeah, D. So this was
Uh,
problem number 3.
this delta P3,
Huh?
how that is calculated? I think the schedule is given as 3, right? 3, and the calculated
Uh,
value. Where is the
okay,
calculated
okay.
value?
Sorry, I did. Yeah. So you have this P3, right?
Yeah, yes.
P3 ka equation. So this is, you calculate it. You put all the values here. C, it is
Okay,
coming out to be 0, right? You 90. This is 0. This is 0. This is 0. So
okay,
directly,
okay.
so 0 minus. I mean, the you do this, it comes out to be -3.
No, it is
So in
3 minus 0, right? Then this is calculated value. P3 is calculated. That comes to be
the
0.
formula is
It's a schedule minus
assumption.
calculated.
Yeah, assumption minus calculated. So
Okay,
-3
but
-0.
schedule, yeah, I guess since it is a load, we are taking -3 from there. So -3 minus
Yeah,
0, I
yeah,
guess. Okay then.
yeah. -3 -0. Yeah,
Okay, okay.
exactly. So yeah, this is how it comes out to be. So, and now another question connecting to this. So here we have been told to determine the bus voltage after first iteration of bus 3, right? Since this was unknown and it was a PQ bus. So from this matrix only we calculate what is del mod V3. So initially, like, I had a confusion, I mean, there is not a mod sign on this whole of thing, right? There is only a mod sign of on V3. So del mod V3 could be negative, right? And it is coming out to be negative from this calculation. So I mean, V3 was what? 1. V30 we assumed to be 1 since it was a flat Yeah, flat start for the load flow problem. So it comes out to be 0.97883. Pretty simple problem. Okay, so now let us go to, yeah, this is a fast decoupled load flow problem. Okay, so here you see that in this problem, bus 1 and 3, these are generator bus. So this is slack bus. So this is what PV bus, since voltage is known, and this is a PQ bus since we have this reactive and active power. So for this, they have told us to find what is the B dash and B double dash matrices, right? Now, I mean, for starting this problem, you have to look at what is the value of y. I mean, in general, we write y to be what? G plus JB. So this is what conductance, and this is susceptance. So I mean, if you do this, see the derivation of this, we would be I mean only analyzing this value, so the susceptance value. So that is why they have told to find out B and B double dash. So we have to only take a look at the imaginary term of the admittance matrix. So I mean, first we have to construct the admittance matrix of this whole thing. So you construct this. So y11 would be this, y12 would be this, y13. I mean, be very careful with the sign, huh? Because y11 would be the addition of these two, y12 would be the negative of these two. So you have to inverse this symbol, right? And your y13 would be this. I mean, you get this matrix, right? Now as you see, bus 2 was what? It is a PQ bus, and your bus 3 is what? A PV bus, right? It is a PV bus. So if you see for both what bus 2 and 3, as we know, I mean for a PQ bus, PV bus, what are things which are unknown, right? Q3, I mean Q and delta, and for a PQ bus, voltage and delta, right? So both for bus 2 and 3, your deltas are unknown, right? And only for bus 2, your voltage is missing. And in fast decoupled load flow, generally what is done, I mean, see, since in a transmission line we have reactant resistance and reactance, and if you I mean generally see your R by X ratio, it is very low. I mean, it's almost close to zero. That is why the fluctuations of power, the real power, it is I mean, the effect of the fluctuations of voltage in the line, it is neglected. Only the fluctuations of delta, the load angle is considered, and for your reactive power, this delta, this thing is neglected. The fluctuations of voltage is only considered. So I mean, if you construct this Jacobian matrix now for the load flow, you would get something like this, right? So your load flow matrix would be what? J1, J2, J3, J4, and this would be what? Your delta, del delta, and delta V, right? So since P would be only depending upon this, so J2 and J3 would be 0. Similarly, Q would be depending on only delta V. So I mean, these values would be 0, right? So delta P would be what? Only J1 del this thing, and Q would be what? J4 del V. So this is how. Okay, 1 minute, huh? Yeah. So you just go through the derivations, the starting of this. I mean, you would start. Sorry, you would start something like with this only. With this kind of assumption, you would start, and then you would be looking at this kind of matrix, this kind of value. So that is why I have written this statement that for both buses 2 and 3, delta 2 and delta 3 are missing. So now this B dash matrix, this is basically your the matrix related to J1, right? Okay, and this B double dash matrix, it is related to your J4. So now, because see, it is connected with the real power thing, and this J4 is connected with the, this guy is leaving and entering. Yeah, this J4 is connected with the reactive power variation. So that is why I have written that for buses 2 and 3, delta 2 and delta 3 are missing. Since your in bus 2 and 3, this is both related to power, right? I mean, active power. We have active power and we also have active power. And I mean, it is a PV and a PQ bus, right? And for bus 2, V2 is missing. Therefore, for B double dash, you have to look at the matrix which are connecting your I mean, every component which is connecting bus 2 and 3. Okay, so bus 2 and 3 means y22 and y23, right? Y22 and y23, and also your y32 and y33. Only the imaginary terms are, because this is B susceptance only. So when you do this, it comes out to be this value. And for bus 2, V2 is missing, right? Since it is a PQ bus. So you can't take this matrix into consideration. And anyways, we are not considering bus 1 since it is a slack bus, right? So that goes. So only those term which is relating with bus 2 and not with bus 3. So that is what? Only Y21, right? Because you can't consider Y23 or Y32. So Y21 is minus 7.22, which is your option number B. I mean, for solving this problem now, you first try to check what is how this fast decoupled load flow, this matrices are derived. After that, just see my solution. You will be able to. I mean, the things will be much clearer. Initially, I mean, it may be a little, may not understand, but you just go through the solutions, you the how it is derived. You may look at some textbooks also by Professor Devapriya Das only, who is the course invigilator of power system analysis. In his book, it is very nicely explained, I found. So you may go through that. The concept will be clear.
Yeah, okay.
Hmm. So we'll be finishing very quickly, huh? So now let us look at problem number 9. This is a pretty easy problem, load flow analysis kind of a thing. So the incremental cost equation of a plant is given as 0.2 P plus 40. So this is the price of the fuel, right? Okay. So rupees per megawatt hour, whose alternator has a Lagrangian multiplier of 100. Find out the power generated by the plant. So this is the incremental cost equation is given by this, right? So cost of fuel, incremental cost of fuel by the incremental power generated by the plant. So df by dfdp, it is 0.2 p plus 40, and your Lagrangian multiplier is 100. So we know, right? So df1, dfp, I mean, different kind of generators, we know this equation, right? It can be simplified to this, right? df by dp equals to lambda. So from this, it comes out to be 300 megawatt, what the power generated by the plant. And now coming to question number 10. So the fuel cost function of two power plants are the following. So these are the C1, C2. Now where PG1 and PG2 are the generated power of the plants, A and B are the constants. If the two plants share optimally 2.5 gigawatt load at incremental fuel cost of 250 rupees per megawatt, so this becomes your df by dp, right? Determine the this p1 and p2 value, right? So we have this first equation, we know pg1 plus pg2. they have said if the two plants share optimally 2.5 gigawatts. So this is PG1 plus PG2 2.5 2500. Now again, okay, let's first differentiate this. So this comes out to be 0.4 PG1 plus 2A, and this comes out to be 0.5 PG2 plus 5A. And they have mentioned the incremental fuel cost, and it is to be equal, right? I mean, they have, since they haven't mentioned anything whether what would be DC1, DPG1, right? So we take this each to be 250, each of these things. So this is your equation 2 and 3. You have three unknowns and three equations. You solve these three equations, you get your PG1 and PG2. So this was your question number 10. I hope these problems on this Newton-Raphson method was clear, because the Newton-Raphson method and previous week Gauss-Seidel method, these are probably the two most important. I mean, you can expect problems on these things only from this load flow study.
Yeah, okay, it is clear.
Okay, fine. So this is about for this week.
Okay. And can you just go to that my question of, or can you open the previous PDF? If you want to stop the recording, yeah, you can stop it. Then
Yeah. Okay, fine. You mean this
I
week
just wanted to see
7,
that.
right?
174 degree, right? That
Okay,
174
okay.
degree.
Wait,
How
wait,
you?
wait.
Yeah.
Yeah, yeah. Let me just stop the recording.